I remembered. So yeah, I was almost hesitant to give the example I gave last week in office hours because it was almost identical to a midterm question, which was you have, but it was different enough and the problem was hard enough that I felt safe. Okay, so we have this, which is non-regular. Not going to be legible. People who might have very small screens. So let me just write bigger. So this is regular. I mean non-reg. Non-regular. Okay. We want to union this with some L prime that is regular. And we want to say that L double prime that comes out must be non-regular. Okay, so your proposed solution was the following, that there exists a subset of L double prime that is this, right? That's definitely true. That subset, but the machine that it's something that accepts this will have to accept that whole subset.
Yeah.
Right? So thus, this must be non-regular because a subset of it is non-regular. Is basically the argument, right?
Yeah.
Right, okay. So here's the flaw with that argument, which is consider so this is, what do I mean when I say this? So I'm going to say the language that equals this, which is all strings, is everything.
Yeah.
Does there exist a non-regular language that is a subset of that?
A non-regular? Yeah.
Yes.
Yeah.
Is it regular?
No. The whole thing is not regular, is it? Oh, it is. It's not a regular expression itself. Yeah.
Or whatever.
Yeah.
And then make it an exception.
Yeah. Oh, yeah, that's interesting.
I don't think it'll be alone in that answer. I didn't grade that question, but none of the graders, none of us were like, oh yeah, everybody came in and destroyed that problem. So yeah,
I mean, it sounded so true, but I didn't think about that.
Yeah, that's the thing is this is kind of gets back to that pyramid-like approach of solving problems, which is okay, so your statement is based on the statement that if a language has a subset that is non-regular, it is non-regular.
Yeah.
But we don't know that from class, right? And so then you kind of have to reprove it or risk this issue. How's it going?
Huh.
So we're talking about the problem on
The midterm.
yes.
Yeah, the last one.
Yeah.
I could not do it. I was
like,
nope.
yeah.
What's up?
We're talking about the last midterm problem. Everyone enjoyed it.
I just didn't do it. I just didn't do it. I was like, nope.
Can we talk about homework, last problem?
Yes. Let me. I'm going to talk about this one more time since I already have it up on the board, and it's a pretty short explanation, I think. Also, I want to give you the right answer, right? Because unfortunately, this is not the right answer. So we're talking about the last problem on the midterm. How do people feel about that one?
I looked at it. I was like, nope. I just didn't.
Fair enough. Yeah. I've definitely done that. Honestly, the grader will appreciate that more than because of this and that and maybe this.
Sure.
It's a this. We don't mind it when somebody doesn't actually know that's wrong, but clearly some people just have no idea what they're talking about.
Hoping for partial credit.
Yeah. They're like, oh, can I get a point?
You're welcome.
Thank you. Yeah. There was actually a professor at University of Rochester who would put in his syllabus slides when he was talking about his syllabus, he was like, for homeworks and tests, if you write, I don't know, for any answer, you will get 15% credit on it.
Oh.
Because he just didn't want to deal with it, which I thought was actually brilliant, right? If you knowing you don't know the answer is better than knowing nothing already, honestly. So and 50% of the credit is not going to get you through the course, so on every question.
Right.
Anyways, so for the last problem, one proposed solution is that because this has a subset because so this obviously as a subset has this, right? So as a every string in this language, in this non-regular language, is a subset of this language, right? Sorry, this is the question. So if you could build a machine that accepts this, it's accepting all the strings in here, which would make it non-regular. Why does that argument not work? And if you want me to repeat any part of the argument, let me know. Does it make sense what I'm saying? I'm basically claiming that because this has a subset that is a non-regular language, it must be non-regular.
Well, because of the second part of the question, right? That was like the opposite of that.
But why doesn't this argument work? What's a counterexample to this claim? That any language that has as a subset a non-regular language must be non-regular.
The language of all strings.
Yeah, that's the. She's like, I wish I thought of that. Yeah, no. So the language of all strings is the counterexample to this. That probably the easiest counterexample at least. So right, because that is definitely regular. You just build a one-state machine that is an accept state and that circles back to itself no matter what it reads. So it's regular. Every language is a subset of it. So yeah. Do people have any other ideas? It could be a high-level idea. It could be specific. So, what are regular languages closed under? Let's start with that one.
Complement.
They're closed under complement.
Concatenation.
They're closed under concatenation.
Union.
They are closed under union.
Clean star.
Union. They're closed under. There's so many. They're closed under clean star, and they're closed under what else?
A lot of other things. Prefix, suffix.
Let's just stick with these. There's definitely enough tools on the board already, so I think we can stick with these. So what then would be the issue with how can we get a proof by contradiction if we assume this is regular? This could be any regular language, right? And this should always end up being non-regular. But if we can make a certain assumption, if we assume that this is regular, we can show that actually then this is regular, which is a contradiction. Okay, so that's going to be that's the structure of the proof. But how would I be able to do that using some of these tools?
Wait, so are we trying to say that we're assuming by contradiction that if you union a non-regular and a regular, you get a regular? And then we're just
No, let's do all we want to use. So we're only going to use that regular languages are closed under these.
Mm-hmm.
Okay? Then the structure of the proof is going to be this. Let's just make an outline. Okay. First step is assume L double prime is regular. Next step, something from here. Last step will be then L is regular. Why am I writing that name? And we're going to use something from here, and we're going to use L prime and L double prime somewhere in here. still not supposed to be trivial.
Okay. Wait. So if you so okay. So if you union L prime and L, then you get something that's regular.
So we're assuming that this union gives you something that's regular, L double prime. That's the first step.
L is non-regular, it's a contradiction. So therefore.
But why is it a contradiction?
Because we said it's non-regular.
So,
no, okay, never mind.
So the whole thing we're trying to prove, right, is that if you do union a non-regular language with any regular language, you will always get a non-regular language. That's what we're trying to prove, right?
Right.
We want to prove it by contradiction. We're going to assume this is regular,
Yeah.
which is what we think is false. Then what we're actually going to be able to do is show that if this is regular, then this is regular. But this we know is non-regular, so that's a contradiction, and thus this must be non-regular. Our assumption that this is regular must be false. You can think of proofs like this as when you have like multi-layered assumptions, things can get sort of complicated. Okay, I'm going to leave only most of these don't matter, honestly. So let's sort of clean up the field a bit, because only two of these actually matter in this context, which is closed under union and intersection. I'm actually pretty sure only one of those matters. I don't know. Let's see in a sec. But what I want to show is basically you can think of this proof as this, right? To prove this statement that a non-regular language union with a regular language gives you a non-regular language, the first thing I'm assuming is this is non-regular and this is regular, right? Those are my like initial assumptions given by the question. You can think of those assumptions as kind of living in, when I think about proofs, I usually think about this, I can't remember the name of these brackets, but you can like get them in tech if you really want. But basically we put up here your premises. In this case the premises are L is non-reg, L prime is regular. You don't have to do this for your proofs by any means. I just think that this structure is very helpful, especially for understanding how assumptions work. So now I'm going to assume, and they help with proofs with contradiction because of that. I'm going to assume that L double prime is so you can think of each line as like saying something that's true. But what I want to say is when I'm making this assumption, I don't know that this stuff's true. I don't like this statement. That's the way to put it. Before I assume this, I can't just use this statement. Oh, sorry. I want to assume it's regular because I want to arrive at a contradiction. But now I'm going to say down in this universe, like in this part of the box, I can use this statement as if it's fact. But what I'm going to do is I'm going to like write facts down, and I'm going to end up with some statement like, I don't know, S and not S. I don't know if you guys are familiar with this sort of notation. You guys are familiar with these? Okay. So this is a contradiction, which means that your assumption here must be false, and now you move back to this universe. So basically, like, I can use that all three of these statements are true. And that's how I'm going to arrive at my contradiction. And when you arrive at the contradiction, you take your most recent assumption and you say the opposite of it as like something that's true. So even though like these are kind of like basically just assumptions, and this is also just an assumption, the order we're assuming them kind of matters. Maybe this was more confusing than helpful.
The most recent assumption, like how that.
Yeah. So basically, like think about it like this. Let's say I told you like there's a ball in some bag, and I tell you, like assume the ball is blue, okay? And now for everything else I say, I want you to assume the ball is blue. Now I'm going to say assume the ball is red. You know that's false because I've already told you the ball is blue, so it's not red. So under the assumption that the ball is blue, you can say that the ball is not red. You can say this other assumption is false. So basically, under these two assumptions or premises, I'm going to be able to say that this is false. So even though it's like, does that make sense? Like because these are like the part of the question I'm trying to prove these two things imply this. Which just means that from these two truths, I should be able to arrive at this truth. And on the way, I take this assumption and I start living in this little universe where this is true. But eventually, I realize that this whole idea that this could be true while these are true is totally BS. And then that's what lets me go back to this world where these things. Does that make some sense? I don't know if that's
Yeah.
more confusing. If this is more confusing, just erase it from your mind. If this helps you a little bit with like structuring, realizing you can kind of like end up, if you keep assuming things, like if you end up at a contradiction, usually that only like nullifies your most recent assumption in some sense. Yeah, there's like a hierarchy of assumptions. It's a little weird. It can get very complicated. Okay, but back to this. This question is not so complicated. The first step is that we're doing this. Then I'm saying you need to use one of these two, the closure property of one of these, plus something about L double prime, and then you're going to get as a implication that L is regular. So really your contradiction is this. L is reg. Right? So I have L is non-regular, L prime is regular. I'm going to assume L double prime is regular. I'm going to say one line basically, and I'm going to arrive at this line. But these aren't contradictory, right? So my assumption must be false. That's kind of the structure this goes by. Okay, so basically the way this one works, does anyone have any ideas of how to use union or intersection closure properties?
I mean, like if the union itself is regular, then mustn't like each one also be regular?
No. Yes, we know that from this statement, but we don't. But we're trying to prove the statement. Does that make sense?
Yeah.
It's one of these things where it's so simple, it can be kind of hard to prove sometimes.
Yeah.
Right? Because it feels like obvious, but it's hard to formalize that intuition, like why it's obvious. So here's the reasoning. Assume this is regular, and then take the intersection of L prime with L double prime. Both of those are regular. And regular languages are closed under intersection. Take the intersection of, what was I going to do? Oh, the intersection of, so if this is regular, then I want to take, do I need complement for a second? Let's see. So if that's regular, and I take the intersection. God, give me one sec. I just want to make sure I don't say the wrong thing. I'm pretty sure I have it. I just want to take a moment. So, if L double prime is regular. Okay, so how is the best way to do this? Because why is this silly? That's slightly harder than the one I gave last week. If you take the complement of L prime and then intersect it, it removes everything from L prime, but it also might remove some things from L. So that's not the best tactic. Yeah, so if L is regular, and there's a machine. Except that there's also a machine. Right. Okay. So there would be sorry, the initial answer I thought of isn't quite right. So here's one thing that might get other people's brains working, which is, think about this. If I take L prime intersected with L double prime, this should still be regular under my assumptions, right?
Yes.
Right. The only problem with, so this is almost the right answer. The problem is it might also remove some things that were in L initially. So this isn't necessarily equal to L, right? intersection with a regular language should be regular. So let's think of another question. The intersection with is the intersection of a non-regular language and a regular language regular?
But it's the same as this one.
Not necessarily.
And you can use this to prove that.
Yes, that's true. Yeah.
So I don't know if you can use that.
What's the simplest way to do this? Give me one sec. What was the other question you got? I'll answer this in one sec. I think I just want to check one thing. Someone had a homework question, right? As well?
Yeah.
I just like don't really understand like the derivative stuff.
Mhm.
I really understand that in class.
I see.
But also number 3 looks like a lot.
Looks ugly, yeah.
Okay, maybe I just don't understand the
At
rule.
least for taking the job.
Oh. No wonder I can't do this. Because this is finite, right?
Yes.
Okay, that's hugely important. I was like, wait, this is the trick. Why isn't it working? Where's the I didn't see where I put it. There we go. Okay. Finite and regular. That's a huge difference. Sorry. I just
Well,
want
I think L is fine. Yeah, L prime is fine.
L prime is finite,
Yeah,
that's
yeah,
huge.
yeah.
You can't do this isn't gonna work. But what is gonna work is to say, okay, now why is this helpful? I was like, this is totally the statement I used to prove it when I looked at the midterm, but now it's not working. So if L prime is finite, what's the size of this language?
Isn't it?
No bigger than L
Let
prime.
me just
Let's say union. Oh wait.
So,
L intersect L prime intersect L double prime.
Right, so you need a slightly more complicated expression. What you need is, this is what I was trying to build before but couldn't build because it's not fine, because it wasn't finite before. But you need, you need the following. Then L union you do just need these two though. Intersection with L prime not. Whew, what a series of parentheses. Union
I know.
with L. Oh god, it's gonna go off the board. Okay, I'm just gonna say it though. It's L union L intersection L prime. Whew.
Did anyone get that right on the test? Because I would
I
never
don't know.
have come up with that
So basically,
unless I was like a genius and knew this already.
so think about it like this. So this is doing what I was trying to do, which is that first statement where I say not L prime intersected with L should be regular. Right. So this intersected with not L prime. Right. So this was the first statement I made. Right. This is what was in his answer sheet, but this is just this. Right. I've just given it a name. Because it was here before was L union L prime, which is just what I have on the left side over there, right? So it's this intersected with the complement of this. So the good thing here is we've removed everything in L prime from L double prime. We're basically trying to take L double prime, use operations with L prime, that we know regular languages are closed under. So basically, if I only use these two languages, I'm assuming this is regular, right? And I know this is regular and finite. If I use only these operations, then I should have a regular language, right? So what I want to do is I want to try and construct L as a expression of those two. So how can I reconstruct L using only L prime and L double prime, intersection and union? It's like that, right? I take L double prime to start, and I'm going to try and rebuild this from that. So I'm going to remove everything in L prime complement, right? That's not a bad start. Like, me just throwing up the answer there makes it look really intense. But there's a couple steps here that you just have to take to basically rebuild L from these other two. What's the problem with this, though? It's that L double prime and L prime might share some strings, right? So if I remove all the strings in L prime from L double prime, I don't necessarily get L, right? I might be missing a few things. But what am I going to be missing? I'm only going to be missing the things that were in both of them, right? Strings that are in both of them. But because L prime is finite, L intersect L prime. So because L prime is finite, what can I say about this intersection?
It's finite.
It's finite, which means what?
It's regular.
It's regular. So this is regular, which means I can take this operation and this is regular, right? Because of our assumption. We've assumed that this is regular. And this we know to be regular because regular languages are closed under complement, right?
Okay.
Does that make sense so far? So this.
Oh, so that whole thing is regular?
The whole
this
thing
would
is
be-
regular and it's equal to L.
Oh, but that's a contradiction.
But
because
that's a
L is not
contradiction. Yeah,
regular.
yeah. But this is what I was missing. I was like looking at it and I was like, this is straight up not true because like I can't add back the things that they shared. Because what if the things they shared was some infinite weird set? That's not necessarily clear. But because this is finite, their intersection will be finite. And that's how you can get regularity there. Whew. Question 3. But do you guys see how, like, I want you guys to feel like this is an answer you could come up with in the future. And I
That's
don't
hilarious.
feel right now that that's the energy in the room is not one of confidence in being able to answer such a question in the future. So let's see. How best to describe attacking such a problem in the future? So proof by contradiction, I think a lot of you might have thought of when you were looking at the test. Let's see, show of hands of who people don't have to say, but I know you thought of proof by contradiction, like you thought it reached a contradiction, and so proof by contradiction is always a useful tool. Past that, to get the contradiction, you usually assume the opposite, right? So this whole assuming that L double prime is regular, like defining an L double prime that is this thing and saying that it's not regular is hopefully a step you might consider trying in such a situation. The hard thing is all this, right? This is the tough part. And I think it gets back to thinking about, okay, what is in this question? It's a question where all I know are these languages are regular. I know almost nothing about them. What do I know that relates to very general regular languages? And there really isn't much content in the course that is this general, right? He actually does this on purpose. Like he will specifically, if a question is more general, part of the reason it's more general is to make sure you don't think about the wrong thing, right? Questions in real life are actually harder than this in some sense sometimes because you might try DFA or NFA related things or like pumping lemma related things if the structure of the question was way different. Like you could have asked about a certain subset of the non-regular languages and say, show that the union with some finite regular language is going to be non-regular. That would have been harder in some sense because you start to focus on the details of L, and the details of L don't matter for the proof. Does that make sense? So when he makes it this general, he's actually in some sense restricted the number of tools you have access to. And so is there anything else in the course you guys can think of other than closure properties that really relate to regular languages in a general sense?
Just like they're finite. Wait, are some regular languages not finite, or are?
There are definitely regular languages that are not finite because great counterexamples to almost everything, or to like great sanity checks. So when you try and say something about regular or non-regular languages or about languages in general, some really good languages that are sanity checks are the empty language, the language of everything, which is non-finite and regular, right? So that's infinite and regular, so that's a counterexample to that thought. And another example is finite languages. If you check these three things and consider, like, if you're trying to say something general, but you consider, it's okay, don't worry about it. It's just been finicky today, so I was like, I don't want to fix it. So if you check those things, I don't remember what things I was talking about.
Okay.
What things was I talking about?
Like
Types of languages.
Counterexamples.
Yeah. So empty language, language of everything, finite language are excellent counterexamples because they have very generic properties that are useful. Does that make sense?
Yeah.
But on a test in particular, this question is quite hard, right? Because it's hard to like review in your mind everything you've thought about and think about what relates to such general regular languages. Anyways, anyone have any questions about this or concerns about this before we move on to other things? Because I'm sure people have other questions. I've probably already spent more time reminding people of a terrible question than they wanted.
PTSD.
Yeah, PTSD. Exactly. The first question almost did the opposite of this question, where it gave you a tool that you didn't need, which is it gave you NFAs. You didn't need where you can get away with DFAs, and a lot of people got sidetracked by the NFA part, where they try and
But they're
that
like
is-
the same, so it doesn't really matter which one you use. That's like
Yes.
that kind of like.
But that's doing exactly what I was saying, makes questions harder, right? Where you give people details that they don't need, which gives them more tools.
That's
When it's
true.
actually better if you have less tools
That's
because
true.
then you don't have many options.
That's true. It's fair.
So definitely, I think a lot of people got a little sidetracked and confused by the NFA stuff, but it's fine. Anyways, though NFAs did actually save a lot of people in another way, which is that a lot of people forgot to define transition functions on every state for every symbol.
Yeah.
Because like just because you don't just because you have a state that you don't really care what it does on 0 and 1.
Yeah.
If you're in a DFA, you still have to define it.
Right.
Does that make sense? So like in NFAs, the way he has defined them, if some branch gets a transition that isn't in the state it's in, so if I have one of my branches is in here from somewhere and it sees a 0, it's just going to disappear. That's in the NFA definition. For DFAs though, everything needs a transition from somewhere. So NFAs actually helped people in that respect, but people tried to epsilon transition and stuff, which was not helpful. So let's see. What do people have questions on? Let's go to the homework for a bit, because homework question?
3.
Cool. Which one's 3? Let me take a look.
The
long one.
3 paragraph question.
DFA construction for the concatenation of two regular languages.
You really only need to read the very bottom line.
Oh.
Like that little paragraph at the end.
I want to read the whole thing just to make sure I have all the clues he gave for the concatenation of DFAs with M and N states respectively, which resulted in a DFA of size of. However, if LM is a prefix to
It just seemed like so many possibilities. I don't know.
He said to do it similar to example 11.2.
Oh, really? In which lecture is it?
11.
Okay, thank you.
But I still don't know how to do it. He just said it's similar to that.
Wait, sorry, do you know the date of that?
Um,
Like the 7th or something?
yeah. Aren't they numbered?
No,
Oh.
not on the.
You can go to one and change the
There's
URL.
a single final state with no outgoing transit.
Oh yeah, or do
Such a DFA is called
This is the DFA
non-exiting.
minimization one, I think.
Oh, okay.
Yeah.
Oh, yeah, I guess that makes sense. 11.2.
This
you
prefix
said?
are
Yeah,
easier
like right towards the top.
Okay.
As follows, let A, M, and A, N be the DFAs for LM and LM. Merge the initial state of A.
Sorry, there's more.
Oh my god, this is a long question.
Because you said it's something
Merge the
like
initial state of A with
proving
the final
that
state.
once
of
they're
AM as a
concatenated, the
result
number of
from
equivalence
two states.
classes is still just n plus n minus
Does
1.
not need to be prefix. Arbitrary was that we didn't know if when okay, whether we should exit or not as a result we had to guess. Blah, then we know. Show that for
Which I
all
guess
M
means
and
it's
N
also
greater than
similar, like
3,
the
the
first
upper bound
question.
on the number of states for this
Oh,
construction is tight by showing that a DFA for LM requires M plus N minus 1 states. Okay, well, the thing that comes to mind for me is equivalence classes. Right out of the gate.
Mhm.
States where
I think you could do equivalence classes or derivatives. Like,
star establishing a DFA right, M plus N where LM. Sorry, what is this? What's the notation he's using here at the very end?
Which one? Where?
For LM, he's defining LM
So that's the language of this regular expression?
of that regular expression. Is that what he's asking? Yeah,
Yeah.
I think it is. Cool. Upper bound number of states is type of showing that DFA requires where. Yeah. Okay, so equivalence classes definitely seems like the way to go with this. Give me 1 sec. Did people have any ideas with respects to it?
And there's an example that's almost, I mean, it's the same thing, but
Almost identical.
just different expression.
Sure.
But it just,
Mind if I look at this? Sorry.
sure.
I didn't- Especially with grading the midterm, I
let me
have not
try to
looked well at
find it.
these things. The minimal DFA thing? Sorry, I'm trying to bring it up on my phone, but it's terrible.
The DFA
reception.
minimization.
Yeah, something, there's some example. Which example, one of you said, which example? 11.2, great.
Yeah.
Try to find a DFA yourselves. Okay, LM, interested, L. Okay. Right, so this is my Mayhill and the Road, however you pronounce it, equivalence classes, right? So for this one, we should probably be looking for the same things, right? Can someone read off, so we have LM,
is
LN, LM equals what?
the language of A to the M minus 2 all starred
All starred,
times B.
concatenated with
Concatenated with B.
B.
Wait, you have a 2 there. It's a star.
Thanks.
And then LN is B star plus A B star. Or just the B, it's plus A.
Yeah.
Yeah.
Plus AB star and B star and star. Also, it's a different B. It's not confusing. Plus A B.
No, the B is starred and then it's all to the N.
To the end.
And then the entire thing starred.
Then I need another one for language.
Yeah.
Okay. What's our goal? M plus N minus 1 or something?
Yeah.
Yeah.
Sounds right. Have people even got a foothold on this question? So there's that example, right?
Yeah, I
But-
was trying to do it with derivatives, which didn't work.
Yeah, can I see how he describes the derivative method? This is it right above 11.2 or
No, I think it's in a different lecture.
it's in a different
we're
lecture?
supposed to do it with derivative.
Hmm?
I don't think we're supposed to do it with derivative.
That's a good question actually in and of itself. No connection, that's BS.
Do you want to see the derivative lecture?
No, I want to see his answer for it. I want to see what he thinks is the ideal answer.
We want to.
Can we
Hmm?
We want to.
You're not gonna get it from me, but you'll get. I would definitely point you guys in a more correct direction and point out some things to think about, if it will load, which it does not want to. Let me just switch to data. Screw Wi-Fi.
Think,
Okay, there we go. Let me just take a look at how he thinks the best answer. I'll tell you, it's not trivial. Okay. Right. Yes, that's m plus, it's m minus 2, and then this is n. Right. How do I give hints about finding equivalence classes though without the equivalence classes? That's the real question for today. Without the lots of generalities. I don't remember how the example was, but this one is so complicated, you'll need to break it into cases to some degree, right? And so, what I recommend is trying to think about not like all the equivalence classes at once. Just try and find like some set of equivalence classes, because you might find like, you know, n equivalence classes that do this, or like m minus 5 that do something else, right? Like, try and base your equivalence classes on like some sub part of the string that forces you to have some number of equivalence classes. That is really your best bet, right? Because
so if you just find like one representative string and prove that that requires n plus n minus 1, we don't have to show that there's some other string, or there is no other strings that can require less than that many states.
so for the equivalence classes, if they're all distinct equivalence classes, then they require separate states, right?
Yeah.
So my Helner road is very powerful in this sense, because it's much better than pumping lemma. It just requires a lot more thought. Because if you give the my Helner road equivalence classes for something, think about when you build a DFA. You don't necessarily build the minimal one, right? You could have extra states that do nothing, right? But if you build equivalence classes and two of them are identical, they have to merge by the rules of an equivalence class, right? So you're essentially ending up with a exact characterization of this like optimal machine. Does that make sense? Like, that's why it's different than just building a generic DFA. Because if I build a generic DFA, like, yes, this machine accepts everything, where they're all accept states, right? But this accepts and I just like have the last state loop back to itself. This accepts every string, which is a regular language. Sure, it's a DFA for that. Is it minimal? Clearly not. If I wrote the equivalence classes, like if I wrote the class of things that you'd accept in each of these states, it's they're not distinct equivalence classes. They're going to actually merge, right? Because because the characterization of let's see, what's the best way?
But don't we
Right,
already-
they're not equivalence classes. The class of things these accept are not equivalence classes that are separate. What's up?
Don't we already know that like there's going to be n plus n minus 1 equivalence classes? Like
Yeah.
So like
So you already know that, which is helpful. The problem is figuring out what those equivalence classes are, right?
but like you already know that they're going to be m from
Only-
the first one and n from the second one.
Why?
Well, I mean, you just have to.
If it's n from the first, if it's m from the first one and n from the second one, then it's actually n plus m. So that wouldn't work.
Well, but like I mean, it's going to concatenate. So like the final state of of m is going to be the same as the first state of n. Like that's like the definition of the whole prefix-free merging that he provides, right?
Then you're getting rid of two states.
Hmm?
Then you're getting rid of two states, not one.
Yeah, you get rid of two states and make one state out of it. So that's why you get the n plus n minus 1 instead of minus 2.
So what's that combination state?
It's the end of it's the final state of m and the initial state of n. But like I guess like what you have to do is you have to show that like none of the other states of m will collapse into n.
Mm-hmm.
And I guess that's what I don't really know what to do.
Give me one moment. Mind if I see his problem statement again? I want to see the best way to use his hints without giving
We
things.
just have to show that the concatenation is prefix free.
No, I think you've already assumed.
No.
Yeah.
Yes. So using derivatives would not be the right approach.
Can I see the derivative method really quick? I don't think that it's the right approach though.
One of them, it's this one, right? So all the unique derivatives of that regular expression result in this machine.
Right. That.
Right. So
Right.
if we prove that it has n plus n minus 1 unique derivatives, then we can probably say something like this. But that might be too complicated.
I don't know. Let's try it. Let's give it a moment. I don't think it'll take long to do.
I mean, you can-
But I don't think it works.
Yeah, I was doing it yesterday, and it's easy to do like continuously taking derivatives of like dA,
Right.
but and then you end up where there are m minus 3 derivatives possible, but then you encounter the issue where you can take like there are so many possibilities of, like you could do DAA, DA or and then like DAB and DABB, ABA, like how do you there's because of all the
No, I
possibilities
think you
there.
can use the derivative. I think in fact the derivative method is unless your intuition is extremely strong, I think the derivative method is how you find these equivalence classes. You mind if I take a look at
Yeah, sure.
what
It's
you do and
kind
see
of
if
messy.
That's alright,
So
don't worry about it.
here is where I'm doing the DAs.
Right.
So that's the first one, and then that's like DAA taking the DA derivative of the first one, and then so the like because I already used n, they're like the nth derivative on A
right.
leads you at that, and so you
Yes.
want to get to m minus l minus, or m minus 2 minus l equals
Right.
1, so that it's
Yes.
epsilon not just gone. So
Yep.
then you have m minus 3 options.
Yeah. And if there's so let's see.
But then
So
yeah, I don't know what to do from there.
you applied the derivative method to LM, is that right?
No, to the
Oh,
concatenation.
To the concatenation, right, sorry. And you got m minus 3, and what were the equivalence classes? What are those essentially m minus 3 equivalence classes then?
That I don't know. I don't know how the derivative.
I think you should look at this line right here,
Okay.
the L derivative. What is that really saying? So if you take the derivative of the whole concatenation, take this as a significant hint, I think.
If I take the derivative, yeah, that's what I did. It's 2 minus L. Yeah, that's what I
Okay,
was
right.
doing. Yeah.
What's L?
L is because we already used N, it's the
You mind bringing
Lth
up the derivative stuff?
of,
I apologize for
on A.
continually leeching off your computer.
of the concatenation. So
Yeah,
it's
thanks.
the A.
I just want to remind myself of the exact rules. So how this is the
Um,
derivative method, right?
Yeah.
Okay, we define it.
Alright,
Wait,
well.
what is L?
So if you take dA of Rn, that's what I'm calling like the regular
It's not
expressions
recursively.
of Lm and
I
Ln.
mean, if you need to compute anything.
If you take the
No,
first
no, no.
derivative, then you arrive at R1. So then RL is the 8th derivative of taking the derivative of RL with respect to A. Does that make sense?
I need to review derivatives.
Yeah.
I needed
I
to
don't-
review derivative.
I don't know how derivatives relate to the to equivalence classes though.
So okay. Theorem 13.7 is exactly what I thought it was. I just didn't want to say it without confirming it because I haven't looked at derivatives in a while. But yeah, why don't I just give everybody a minute to read 13.7 because it's highly relevant to this question
That's what I was looking at.
as well. The one he gave is also very relevant. Like the one he was saying is basically this type of question. But to use derivatives to get equivalence classes is basically allowed by 13.7 if you look at it. And this is what I was trying to say about like equivalence classes giving you sort of like a minimal DFA. Derivatives are sort of a method of finding that minimal-ish DFA. Because when you do the derivatives and you get that like drawing, the machine thing he's talking about, each of those is an equivalence class, right? Instead of having the states are each labeled with some regular expression,
Oh.
right? And as you take the derivative, you're basically getting all of these equivalence classes.
So each derivative is a different equivalence class.
Yes, and 13.7 explicitly says that.
But
It's
so
different my hill in the road equivalence
for
class.
the DA
I think it's right under the picture. If you look like at the paragraph right under the picture, it just straight up says it. But if you look at a derivative, if you look at how you take a derivative, I think this is
Yeah,
one
okay.
that you just, like if you do it out, it really helps to try paying attention to it as you do it out, how it separates it into equivalence classes. And if you look at, so when you ended up with this, taking your derivative,
Yeah.
what equivalence classes is this? So this is going to correspond to essentially m minus 3 equivalence classes? I think it might correspond to m minus 2, but that's okay. It corresponds to
Well,
m.
if it depends if you set it equal to that's what I
0.
was 0 because
Yes,
okay.
you do.
Okay.
So it's really m minus 2 equivalence
Yeah.
classes.
So I'm kind of last you here. Like,
Sure.
Why doesn't correspond to like n minus 3 and how do you get there?
So actually, I mean, do you want to talk about it?
Yeah.
Because you've
So-
actually done it.
What you're
Have a good one.
doing is so you have just okay.
You can just
I'll
throw it
put
up.
Yeah.
Yeah.
You're taking if you have like you're saying that this is the regular expression Rm
Mhm.
and this is Rn, then you're taking dA So the first one you take, I don't know if you can see the button, is, I'm calling it R1. It looks like A M minus 3 R M R N. You arrive at the same thing, but just with this factor. And then you take for like R2 equals dA of R1 equals dA of AM minus 3 RM Rn. And then for your lth derivative, so RL is dA of RL minus 1, and you arrive at AM minus 2 minus L RM Rn, and you can take this until, like, what you eventually get at is a when you have the empty set, when you're trying to take the derivative of this again, and it gives you, it just cancels out the whole expression, and so that happens when the exponent is 0. So then you have m minus 2 minus L equals 0, which gives m minus 2 equals L. So you can take it L times, which means there are m minus 2 equivalence classes.
And where does the n kick in? Like when does n?
So it doesn't.
Yeah.
If you like, in this, if you're taking only for A's, because it's RM, Rn, what happens is you do, like, oops, that's RM, Rn.
You definitely don't have to do this to get the answer, but I do think it is a more mechanical, less intuition-based way to solve the problem, which is usually helpful for people. So
But then I don't know how you get the other n plus 1 states.
So think about what you did here, though. Now let's go back to intuition for a minute.
Okay.
So this is helpful mechanically, but then for understanding why this is interesting and how this helps you get equivalence classes,
Yeah.
now the intuition kind of has to come back in, right? So how do you do my hill on the road stuff in general, anyways? Like if I have two pretty obvious things, like let's say that I want to. So can someone describe to me the method you use for proving two things are different equivalence classes? So what do does anyone have any guess what equivalence classes this whole derivative thing is highlighting? It's highlighting something about the A's, right?
It has to do with the number of A's.
Exactly. So
But only in the first expression. No.
But the first expression is part of the total expression now, right? Because they're concatenated together.
Yeah.
So in LM, this number of A's will affect the equivalence classes, right?
Yeah. Because that's what comes first.
It's partially because of that it comes first. It's mostly in that you have a couple of options for it that. What's the best way to put it? Yep. Because consider. Let me give an actual example for this one, because the question is long enough and hard enough that I think that's fair. So, let's try and separate the following two classes. You'll still have to explain it, which is enough of a challenge, but I want to use the same one so I don't confuse myself. Right. two different, let's say, without loss of generality. How could you separate these two? Like, how do you show that these are pairwise distinct? Which is what Mile on the Road's going to require.
Adding something to the end of AK that it makes it be accepted by language, adding the same thing to AL, and that's not accepted by the language.
Right.
So you have to think about the number of characters following it.
Right. So if you think about, so what is in the language? It's going to be something of the form like AM -2 with some other stuff, right?
Yeah.
If I, where does my board end? Okay. If I, so how will I do that? So this is going to be some string here that makes it in
Yeah.
LM,
Oh,
LN.
but
Oh,
if
wrong end. Okay.
but
right.
if they're different numbers, if K and L
Let's-
are just
Yeah, let's formalize this a bit though.
yeah.
So if I pull AK out, then this is M -2
Yeah.
minus K.
Yeah.
Right?
Yeah.
Does that make sense? And there's still this other thing, and I still want it to be in the language. And now, by Mile on the Road, I'm going to try and substitute this AK with an AL, right?
You can. Yeah.
There you go. Distinct.
Sorry. Can you repeat that?
Sure. So I don't want to give everything away, but I think this starts to tell you how to do all of it, all this problem, which is think about K and L between 0 and M -3. Okay? So I can pull that many M's out of here, right? And still have at least one left. Because I'm pulling somewhere between 0 and M -3 A's out of this, okay?
So I think when I was like doing this approach, my confusion was that like the separation. Like, can we separate it to improve that one? You have M in one case, at least M -2 states, and then.
So I think the best way to do this is to try and handle all M -2 states of this form at once. So the equivalence class
and
is
you
here.
Keep like N constant. Like you're holding N and.
Yeah.
Okay.
M is some number that's going to determine the number of equivalence classes. So basically what we're trying to prove is the number of states of a machine necessary to accept this language, where M and N are fixed. But we don't know what they are. They're going to be
Right.
constants. We don't know what they are, so we have to show that no matter what M and N are, the number of equivalence classes scales with M and N.
Right.
Does that make sense?
Right.
So here we've been given some M, okay? And the language is the concatenation of these, okay? So what I'm claiming now is that there are M -2 equivalence classes related to A. Related to this A to the K and A to the L. Where basically I take a string in the language, like this A, M -2, and then some other stuff to make sure it's in the language, right? There's got to be at least a B. In fact, that's in the language, right?
Yeah.
Okay.
So we're not doing this for the concatenation of the.
We are doing it for the concatenation.
So where's the N in this?
Where's the what?
The N.
The N isn't playing a part yet. I'm breaking it into cases. So what I want to do is I want to talk about some of the equivalent classes now, and some of the equivalent classes later.
Okay.
So one set of equivalence classes that seem to be basically that I want to talk about all at once are the ones related to the number of A's.
In the first expression, basically.
Yeah.
Okay.
And so this is in the language, but these are if I want to show that these are distinct equivalence classes for K and L between 0 and M -3, is that right? Or is it between 1 and M -2? I don't know, that's a good question.
For what?
For this K and L, where they're what they range over. Are they
Oh.
ranging over 1 to M -2 or?
I think it's
0
zero
to m minus
because
3?
it's m minus 2 star.
Right.
So then you can have 0.
Yes. Yep. So it's from 0 to m minus 3. So this is good, but it's going to give you m minus 2 equivalence classes, right? And
so why is it to m minus 3? Shouldn't be to m minus 2. Because you can have it. You can have, if one's 0, then the other has to be. Or no, that's not true at all.
because the 0 and the m minus 2 case are going to be equivalent. That's why.
Okay.
So you could do 0 or you could do m minus 2. That's actually the real trick, right? Okay, so basically, why is that? So if I take a to the 0 and a to the m minus 2, why are those the same equivalence class? So if I take 0 a's out, it stays like this, right? If I take m minus 2 a's out, well, it's actually just still this, right? Because there's nothing left in here.
Yeah.
So that's why you wouldn't be able to prove this statement for 0 versus m minus 2. But for everything else, what I want to say is this is in the language, right? But if I pull out k, and I get rid of it, and I try and substitute it with L, what can I say about this string now? Can it be in the language?
No, because it doesn't, like, refactor to m minus 2.
Yeah. As long as you pick the bounds on k and L correctly. Like we said, if you picked 0 to m minus 2, you would have a problem. Because 0 and m minus 2 would actually result in the same equivalence class, right? Yeah.
So then I would say you probably next want to do something about the amount of b's.
That seems like something related to
But
this
to
statement,
that
certainly,
end.
right?
But so,
But these derivatives, I guess, were kind of helpful in determining that this part was of interest in some sense. So, like, these can be helpful. But really, in some sense, I think it's almost mostly intuition. Intuition is certainly how I want to do it.
yeah.
I'm trying to think if you can use derivatives. It's a really interesting question to me now, if I could use the derivatives to say something about this, right? Because the way you took the derivatives is only giving us information about this one, right? It gave you the exact number of equivalence classes you should have related to it, and it essentially gave you the statement right before the end that you wanted to be working on, which is very helpful, right? Because this L is just like the K there, it's like pulling it out. I feel like there should be a way to deal with the derivatives that helps you identify the statement you want to make with respects to this, but I can't think of it off the top of my head. Here's another important point, though.
I had a
Yeah, of course.
question. Would b star plus b star reduce to just b star?
B star plus B star would reduce to B star.
Okay. Because then you get for db.
Because every time you add a B star,
Mhm.
the star can be of a different length.
Yeah.
You know, it's not fixed like m minus 2. Every time you add m minus 2 a's, it has to be m minus 2 a's. Every time I add a star
Yeah.
to my string, it can be any number of a's.
Because
Does
then
that make sense?
for db, you
Mm-hmm.
get b star plus rn every time. But that doesn't really help.
So
that's only one derivative then.
So one really nice thing is this. One of the best things is this b is very helpful, right? Because it essentially bisects your string into two parts.
Right. Yeah.
Anything before a b you can manipulate the a with respects to, but if I put a b down and nothing before it, now I'm essentially talking about ln, right? Like, because if I put, if the first thing is a b, then everything else is this, right? This single b kind of tells me that, okay, this is all ln, right? But if I want to talk about, what's happening here in the equivalence classes as they relate to n, then I just can talk about a string that starts with b and then, or starts with a to the m minus 2b, and now everything else must be in ln. There's no, once you see a b, you are definitely in ln, and until you see a b, you are definitely not, right? So there's this very clear bisection between the two parts of the string, and this is actually extremely helpful for separating their equivalence classes. So you know how you guys kind of see, I think, at this point, how to prove that, and if you don't, interrupt me and we can keep talking about this.
So the first part, okay, but how do we deal with the n again?
So here's the thing. This is in the language, right? a to the m minus 2b is in the language. Are we on the same page on
Yes.
that, onto why? It's because of this star, right?
Yes.
This star in the whole statement means this can just none of
Not
this.
exist. Yeah.
Right, exactly. So, the way I proved these equivalence classes are separate was essentially to ignore ln entirely.
Okay.
I'm still talking about lm concatenated with ln, but
we can
the
specify-
string I'm considering
Yeah.
has nothing from ln in it, which makes it easier to think about, I think.
So like you show that there's n minus 2 in the first one by ignoring ln,
Yes, by ignoring ln.
and then you can effectively do the same thing for lm, right? And ignore that by like setting it as some,
As like a to the m minus 2b.
and then you get some like n or something in the second one, but that's
Something like
like
that.
m plus n minus 2.
So there
Like
I
how do you get the
I
how do
would
you get
say
the plus 1?
there are these things. There's a set of equivalence classes that naturally go together that are based around m and scale with m, right?
Mhm.
There also is going to be, spoiler alert, ones related to n that
Mhm.
scale with n. However, there may be some that always exist, regardless of the setting of m and n.
Okay.
That thus, as long as they're greater than the amount he said, because I think he said a bound on m and n, right? Because you can't take m minus 2 for like less than 3; it's kind of meaningless. So
Mhm.
there is a bound here, but there's an equivalence class that may not scale with m and n. So if you find that you've managed to make an equivalence class that scales with m and one that scales with n, you might want to start searching for ones that are always there and don't scale, because that might happen, right? There are other things in here. Maybe.
I mean, that's the only thing that doesn't interfere with that.
B star isn't an equivalence class though,
No.
because
But it-
B is always in the language, right? So it's not quite that.
Yeah.
There's also always, what else is always in the string?
1B.
1B is always in the string, but
Yeah.
there's at least one other thing in the string. Okay, what's definitely not in the string? What's definitely not always in the string?
A.
Everything here.
Everything there.
Okay,
Mhm.
great. B is definitely always in.
Yeah. A
Uh,
doesn't always have to be.
A doesn't always have to be. It's interesting. Let me see the.
Because epsilon's included in the clean star, right?
Yeah, I thought there was something. Do you have the problem up by chance?
Yeah.
Great.
This one.
Yep. Yeah, that's a good point. Yes, it doesn't always have to be in there. What's the best way to do this?
B is the only thing that has to be in the
B
string.
by itself, is that an equivalence class? Let me think.
I think so.
No, there's a good. There's something good here. Oh, it's really tricky to see it. Why is B by itself not an equivalence class? Because you've already covered it in one of the A classes. A0. A to the 0 or A to the m minus 2, I think, is already covered. So
Yeah.
B by itself. Okay, cool. So here's one of the things that makes this problem so tricky. Yes, you
So
need the stuff
clever.
related to A. I mean, sorry, to M. You need equivalence classes that scale with M. Yes, and you need to prove that pairwise they are disjoint. Right? That A, let's say like M is like 7 or something, that A3 and A4 are different equivalence classes, right? We need to know that for every two numbers. That's what this proof should do, right? Because you say, okay, I take AK out, I try and substitute in with AL for some different L between 0 and M minus 3. Clearly, it's not of length M minus 2 anymore. Do you see what I'm saying? If not, it's fine. I can explain it.
I think my confusion is all about the second part.
So the second part Well, why? So, what's your confusion about the second part?
For example, like, what kind of words can we choose that kind of capture all possible equivalent classes?
If you
So what definitely changes about this string the greater n is? So the b, it's unclear how many b's there are going to be, right? Every time you, so, but what definitely changes about your string that is noticeable as n increases? So the thing that changes about your string that's noticeable when m increases is the number of a's that can be before this first b. There's just no other way to replicate this in the rest of the string. So that's going to scale with out.
okay.
So if I increase, like, let's say that I give you a string. I'm going to give this one. So I'm going to make settings for them and then rigorously do it. Can I erase this? Are we kind of good with this part? Okay. Okay, let's set m equals 3 and n equals 4, and I'm going to give you the following string that is in the language. A, B, 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 A, B. What do I want to do next? And then A, oh wait, sorry, this is way too big. I did n equals 4, which means I need to erase some of this. And the interesting question is why? And then that's in the language right now.
Wait, what?
Yeah, that's in the language.
Okay, so the first 4 terms have to do with ln.
So the
Maybe?
first
Yeah.
3, these are all from
Or
lm, and
Yeah.
importantly, these are from m equals 3,
yeah.
right?
Mhm. And then, so you've got
What in here tells me that n equals 4? Like, why would I know instantly
the
looking
number
at
of
this string?
a's.
The number of a's.
Because you're starring B, but A is only from the number of n's. Okay.
So the reason these equivalence classes worked for A was because you could distinguish, if I change m, it would be very distinguishable what m was by the string I put up, right? Because it would be the number of a's. Yeah, it'd be related to the number of a's. And for n, the thing that n changes is the number of a's after the first b, right? So what did I do here in the application of this? Well, I took b star and I took 2 b's, let's say, okay? Then I took ab, or I took a with 0 b's, and then I took a single b from b star, something like that.
Yeah.
Then I got ABB from this again, and then I got A with no B's and A with no B's. So it's in the language.
Yeah.
And I use this exactly 4 times because that's where all of the A's have to come from. Does that make sense?
Yeah.
Okay. So this will help you find equivalence classes related to n, right?
Yeah.
Here's the real challenge. It's just a lot of effort. You've got to do a couple of things. First, we already did for the A's, showing that they are pairwise disjoint.
Yeah.
For the B, for the ones related to n, and these A's, you're going to similarly have to show that the equivalent classes you define are pairwise disjoint, right?
That in the beginning's completely different from the end.
So if I'm just trying to say that when I define my, have a good one, equivalence classes that scale with n, so I'm going to so this, in here, I got like m minus 2 equivalence classes,
Yeah.
m minus 2 equivalence classes,
Yeah.
which scales with m, right? And I defined them all, and I proved that they're pairwise disjoint.
What do you mean by pairwise disjoint then?
That they are separate equivalence classes. Like,
Okay.
a to the 0 and a to the m minus 2 would not be pairwise disjoint.
Yeah.
right?
Mhm.
You wouldn't be able to do this my hill in the road proof where you pull something out and
Yeah.
you say, I add this new thing in from the other equivalence class and notice it's no longer in the language,
Yeah.
right? You'd have to do that, right? You take two arbitrary equivalence classes from the set you define,
Mhm.
and you show that they're pairwise disjoint by trying to sub something from one in for
So
something
for
from the
0
other.
to n minus 3, they're pairwise disjoint.
Yes.
Okay.
And for something to something with respect to n, those new equivalence classes you define should also be pairwise
Is
disjoint.
0 to n minus 1 then? Because
Maybe.
0 and n.
0 to n minus 1 is close, if not right. It's right or close to it. So it's important to think about it more, and I'm not going to give that part away, but I think that it's a very good start.
Okay.
If it was 0 to n minus 1, it would add n equivalence classes,
Yeah.
and you'd be missing 1,
1.
which could either be in either of those two sets, or it could be something
Different.
that is fixed and does not scale with m or n, which is definitely a possibility.
But the only thing that doesn't scale with m or n is b, is that 1b, but we established that that's in the other equivalence class.
Sure.
Oh no, I was thinking that n is on the full b star.
Mm-hmm.
But it's not. It's only on a b star. It's not on that whole b star plus a b star. So then that doesn't scale. So then, but how does that give you only one more? Because if you have the same, if two expressions have the same m, a,
I'm honestly trying to think of how he found it at the moment.
not right.
Like, he has the equivalence class is finite. I'll give you that hint. Because an equivalence class doesn't have to be infinite, right? It doesn't have to be
Yeah.
like some.
I mean, infinite is not gonna be regular, so just wouldn't work.
Equivalence classes can still be infinite, though.
No,
I mean, a to the I.
like I mean, it wouldn't be regular. I mean,
Hmm?
like if you have like infinitely many equivalence classes, it's not gonna be a regular.
No, infinitely many equivalence classes. I'm saying the number of elements in your class
Oh, yeah.
can be finite or
Right.
infinite. Does
Right.
that make sense? So you could like take some weird substring that might appear that is finite, and it might be its own equivalence class.
Mm-hmm.
For example, if there was a string that no matter what that is in the language, but no matter what you add to it,
Mm-hmm.
it's not in the language, then it's its own equivalence class.
A string that's in the language, but if you add something to it, it's not.
Cause I'm trying to think. What's the exact wording of the proof method he used for this for My Hill in the Road? Do you mind bringing that lecture up really quick?
With the My Hill in the Road lecture,
Mhm.
this is when he talks about those equivalence classes. I don't know which one.
Where does he? This is DFA minimization though. I'm looking for his
Oh.
definition of My Hill in the Road
Oh, okay.
stuff. Because I want to just. Ideally, I would like to phrase things the way he would if I can.
Yeah.
So it's got to be right invariant. Okay. So you can take something out from the beginning and substitute something else in.
Oh, there's the what he defines.
Right. We define the relation, blah, blah, blah. Is the My Hill in the Road relation. So basically, if I take something out of this class and substitute something else for it in the class, then I should be able to still be in the language. And then, like, if there's a finite
Yeah.
string that is in the language,
Mm-hmm.
but no matter what you substitute, if you took any element from any of the equivalence classes. So notice our first equivalence classes.
Yeah.
Suppose we had a finite language. I mean a finite equivalence class with, let's say, one string like A, B, B, A. I know that this is not in the language.
Yeah.
But actually, is it?
No.
It could be. Depends what M and N are.
Oh yeah, it could be.
But anyways,
Yeah.
putting that aside, let's say that like I had A for M. Like if I sub because one of my equivalence classes might be like A to the 3, right? But this by itself is not in the language.
Yeah.
So if I took out the only member of this equivalence class and tried to substitute it in, it instantly would not be in the language.
Wait, say that again?
So think about it like this. If I gave you this string, let's say that this is its own equivalence class. It isn't, because it's captured by some other equivalence class. Probably the one related to the ends. Certainly it's not captured by any of these.
Yeah.
But if I tried to substitute this string out for this in anything, then what you get will not be in the language because you just have like all A's. What's a better way to say this? It's really hard to give an example of this.
So the idea of the equivalence relation and how it relates to the number of states is that you'd have to, if you're out of some state, you could sub it out, which I guess is what you've been saying.
Yes.
So that makes sense.
Basically, if you have some, what is it? I guess it's like a suffix, or is it a
Yeah.
prefix?
Prefix.
Let me.
We define the relation for all words x, y are equal if they both have the same suffix that would.
Yeah.
Yeah. Right, because for the defining the A, going back to the A equivalence classes, which are easier, I should say. I'm defining this. I really like the basic definition of My Hill on the Road. I think it is very, much easier to understand. Which is just that if I take M minus 2 minus K
Yeah.
to be with B, right? If this is my Z, then two things are in the same equivalence class. If adding them in front here would make them in the language.
Yeah.
So certainly AK
Yeah.
is going to be in this equivalence class, but AL would not be, right?
No.
For a different L that's between 0 and M minus 3. Because if I try and sub it out and attach it to my Z, I want to separate them clearly from Z.
Yeah.
Then it won't work. So that's why they're in different equivalence classes, right? But something like this, what is in that equivalence class would be this actually. M minus 2 plus K. Right? That is in the equivalence class.
Yeah.
Right.
Right.
So that's like so that's what this equivalence class then of A K is. It's all of these. It's gonna have all of these strings.
So it's.
And let's get back to why does this define a minimal DFA?
Mm-hmm.
Why like when you do the derivation and you get these like weird regular expression things, why do these describe some minimal DFA? The reason is because, did I go off the board again? Damn it. 1 second, I'm just gonna write this really quick. What was it? A, K, A-L, and I'll write that last one down here if anyone, A, M minus 2 plus K, and then you have your Z is equal to A, M minus 2 minus K, B. Right, and so this one works, this one does not, this one works. So these are in the same equivalence class. But not this one. Okay, now what was I trying to say before? I lost my train of thought.
About how it relates to the minimal DFA.
Right, how does it relate to the minimal DFA? Thank you. So, the reason it's interesting that for the same Z, it's either always in the language or always not in the language. Like everything in this equivalence class, for any Z, they're either going to be, like if I took Z to be this, A.
You repeat it.
If I took Z to be this, then if I took as a prefix either of these, would it be in the language?
Well, it depends on what M is.
It actually doesn't because there's no B's in my string, right?
Oh,
Right?
okay,
Like
yeah.
if I
Yeah,
took
yeah,
a to
yeah,
the k, and it's also the wrong number of a.
Yeah, yeah, yeah.
It's so like a to the k plus
Mhm.
one other a is a to the k plus one a's, which is definitely not in
Yeah.
the language, right?
Yeah.
But notice that no matter what I put these in front of, it will be in the language or not be in. It'll be in the language or not be in the language, and it depends on z, not on your choice of element of from the equivalence class.
Yeah.
Think about that for a sec. It's
Yeah.
a really helpful observation. So if this is my x from my Hilton row from the definition, and this is my y,
Mhm.
then x z
Mhm.
and y z
Mhm.
are either both in the language or not, or
Yeah.
both not in the language for any z, and for any two x and y from this equivalence class. Does that make sense?
Yeah.
Cool. So the reason this is amazing as a property is think about it in terms of a DFA. If you think about it in terms of a DFA, when is this a really useful property? When you're trying to, I'm going to erase some of this if you don't mind. So this is useful in a DFA because think about if I'm in this state, okay? And I tell you that, what's the way to put it? If I have an x and a y, such that no matter what happens after this x and y are read in the DFA, I should either accept both or reject both. Then reading these x and y should get you from the start state to this state.
The same state.
Right.
Yeah.
Because it doesn't matter how you got there, right? The z should lead you to the same place. So every equivalence class requires its own state, right? Because if, let's say, two things are not in the same my hole in the road equivalence class, for example. Let's compare the opposite example, where two different x and y with the same z could lead you to different places.
Yeah.
Then they definitely can't be in the same state at the same time, right?
Yeah.
Because for some z, one of them needs to go to place, A, and the other needs to go to place B, and one's an accept state and one isn't. So that is bad, right?
Yeah.
So every equivalence class is exactly a state, right? It's yeah, that's it. That's all there is to it, I guess.
Yeah.
So my hill in the road is a little complicated and weird and finicky to work with at first, but it's actually a very beautiful way to create minimal DFAs. Yeah, and so he's already proven that you don't need more states than m plus n minus 1 states to achieve this prefix free thing, right? But now what he's trying to get you to prove is he's making you actually build the machine. He's not saying build the machine. Because building a machine does not tell you that it's the minimal machine, right? Like just because I build a machine that works, it doesn't tell me it's minimal. But if I come up with the equivalence classes and I show that for each of these two equivalence classes, exists a z such that that sends strings from their equivalence classes to different places, I know I need those two different states, right?
Yeah.
So if you can show that there are n minus 1 equivalence classes, then and they're all disjoint, then you must need at least that many states, right?
Yeah.
And he's already shown the upper bound of the number of states you need. So then you would know exactly how many states you need to achieve the machine that is the concatenation of lm and ln with these properties. Does that make sense? At a higher level, why this is interesting and why he's trying to get you to do this, and hopefully does this make a little more clear what the my hill in the road equivalence classes are and like the derivations?
Yeah.
They're all really deeply connected, but it's all such different ways of doing things. You're I don't know. Like when you're trying to do DFAs, you might just be trying to come up with it from scratch. When the derivations, you're just maybe mindlessly following rules and not seeing what they do. When you're
Yeah.
thinking of the equivalence classes, but they're all really connected, which is why the derivations gave you something interesting with relation to this problem. So the other thing I wanted to say though about actually solving this is how we showed that all the AK classes are disjoint, AK and AL, from each other between this range of K and L between 0 and n minus 3. We're going to have to do something with the N classes, similar,
Yes.
right? Not only are we going to have to prove that they are disjoint from one another, we'll have to prove that all of the A to the K equivalence classes are different from the classes defined with respect to N. So
Yeah.
Can anyone think of what the n different equivalence classes for before we go?
The n different? What should
So
we-
how can we create a set of equivalence classes that is scale with n? We basically tiptoed right up to a specific example.
Well, couldn't you just?
I'm gonna erase a lot of nonsense to just declutter the board so we can get back to something simple, which is that we have equivalence classes right now for everything. Go away. No distractions. Oh, okay. So we have.
Couldn't you give them the same prefix, or can you not?
So we have a bunch of these for different settings of k.
Mm-hmm.
Okay, what's your prefix?
Can you have a m minus 2 star b?
We don't want a star because we want something specific. It's easier to go with specific.
Okay. I mean,
So-
if you can just drop it, then sure.
Let's just drop the
Okay.
star. So
Then b, if you have a b
Mhm.
there. Then I guess you don't really need the b star in the beginning. So can you just have a to the a b star like k?
do you have an idea? Any idea of what we could do to? So what did we say told us how big n is in the string? When we had that string up before, of like a, b, a. How big would actually that's not a good enough example. Like how big would must n be in this for this string to be what it is? So for m, we know n is 3, right? Because there's 3 leading. We know m is 5, right? Because there's 3 leading a's.
Oh, the number of A's.
Right. So n would be what?
3.
Exactly. So what might be when the number of a's was what defined these equivalence classes. How did we do it? We just gave an a to the k, which ranged from k between what?
0 and m minus 3.
Perfect. Okay. And so how might we be able to define the equivalence classes then that relate to n? So this so this is a good start, but we'll need something here that kind of defines each equivalence class and has a range that scales with n, right? The answer is probably less complicated than whatever you were thinking.
Just
Right.
an A to something?
It's going to be on a different range.
Yeah. Zero to n minus 1. I mean, the logic has to hold then.
So if it's 0 to n minus 1, then you only have m plus n minus 2 equivalence classes.
Yeah.
And there might be more. Well, you
There's
should have at
one
least
more.
one more.
But yeah, only one
We're
more.
pretty sure we didn't miss it in the a's, right? We've talked
Yeah.
about the a's enough that it goes from 0 to n minus 3, and that's just a fact. The conjecture right now, from you at least, is that n ranges between 0 and n. That the
Okay.
next set of equivalence classes ranges from 0 to n minus 1, right? Which is plausible.
I don't know. I feel like it kind of has to be 1 to n to. I
Did-
feel like you have to have an n.
Did we consider the just one B, just that word?
Hmm?
The word that's just one single B. Did we
Mhm.
consider that?
Yes, it's actually in this equivalence. Weirdly enough, it's in this equivalence class. Or if you prefer, this equivalence class, I guess.
So
Like just a single B, isn't that?
Yeah,
How?
because think about the following z. Z equals b. Okay.
Oh, yeah, B.
And now you can put in am minus 2 a's, or you can put in 0 a's. So it's actually like very
That's true,
strange.
but yeah.
Yeah, it's a little weird. Well, actually, so we're saying that B is in that class. So yeah, if I added a B to this, I would have BB, which is in the language, or I could add a to the m minus 2.
Wait, why is BB in the language?
It's this B and then this B,
Okay, yeah.
or though n is yeah. Because this can happen 0 times.
Oh, not necessarily actually. Because they can be fixed, could be any n, right? So it doesn't have to be a 0.
The thing is, every time n occurs, so to be exact, right now I'm oversimplifying
Yeah.
this statement, because essentially what's really happening is there can be. This would still be possible for n equals 3, right? In fact, this would still be possible for n equals 3. Why? Because the star can happen any number of times. Let's say it happens 2 times. The first time, I do this 3 times and get this.
Yeah.
Second time, I do it 3 times and I get this, and it differs, right?
Yeah.
The equivalence classes we talked about will still capture this
Mhm.
somehow, and that's important, but yeah. Anyways, the single B gets dealt with, though, by one of the A cases. Yeah. So yeah, it's a tough problem, because not only do you need the disjointness of the new set, the A to the m minus 2B, I think you can, yeah, A to the m minus 2B A to some K, right?
Yeah.
You still need to actually prove all of those are disjoint from the A classes, right? I need to know that A to the K and A to the m minus 2 B A to the L are different
Yeah.
for everything within their range, right?
Yeah.
These need to be I need to show that these are disjoint equivalence classes as well. And you can always fall back on like the basic Myhill-Nerode definition for that sort of thing.
Yeah.
Does that make sense? Yeah. I think I'm out of time today. But yes. So
Can I ask you like a very quick
Sure,
question
sure.
about question 1?
Mhm.
So this is my proof. It's like a couple of lines, and I'm sure it's wrong, but
what's the first question? Bring it up first.
so it's here proving that the palindromes over is
Over AB, show that every
Yeah.
word in in AB star is in its own Myhill-Nerode equivalence class.
Yeah, mine was
Oh,
super
yeah.
short too.
Show that every word is its own Myhill-Nerode. Okay.
So if we just pick any x and y,
Mhm.
this is always gonna distinguish it. This is gonna distinguish the two, because these two are nil, but these are not.
Yeah.
So the whole thing, like, is this gonna be?
So I mean, let me. I mean, your idea is completely correct. It's not a You're right. The
Right.
Z only works for what?
For x, right?
For Z reverse, right?
Yes.
Yeah, exactly. So like, X needs to equal X needs to equal Z reverse,
Mhm.
and if it doesn't, then it's not in the language.
And
Right.
this can.
And so if you take out,
Yeah.
so if your equivalence class is just a single string,
Yeah.
you're saying that Z will be its reverse.
Yeah.
And if you drop the X and try and replace it with anything else, it's not
It's
the
not
reverse.
gonna work.
Yeah.
Yeah.
It's this because, yeah.
Okay.
So, I mean, I think your idea is perfectly correct. I would add like an English explanation maybe to make sure that, the grader doesn't misunderstand. But yeah, I mean, it's a fairly straightforward one. I mean, you can even say, because it's a different string,
Yeah.
certainly if it differs in length, then, let me see, what's a more formal way? Is there like a nice way to make this super formal? Because what if, so AB where W equals W reverse, so
What?
Have you done problem 2?
Yeah.
How, I've done the derivatives,
Own.
but then how do you take, like, use that
So it's
to
all
construct
strings that
the
equal their
minimum
own
DFA?
reverse.
Oh, I just did the same thing.
This is
because
not
I don't know
quite
if
the
it's
same
correct,
question,
but
is it?
I
Let's
just
see.
did the same thing. I
All
did
strings that
because,
equal their own reverse means
just like this
that.
thing.
Oh, like each state is
So-
one of these things? Okay, cool. They look so funny.
Yeah, it's kind of janky looking, but
Yeah.
I think it's fine.
Okay, cool.
This, so Z is, I guess, empty is what you're thinking?
It could be anything, like you can pick whatever X you want and then just the reverse of it.
Oh, you know what? So what you really want is, for some string, let's say like 101, it's in the language, right?
Yeah.
Because it is its own reverse, and that's what this language is defined to be.
Yeah.
Yes.
So, what's a good Z to pick to show that this is its own equivalence class
Itself.
right? So if you pick Z equal to 101, then certainly this in front of it, it's its own reverse, because it's
Yeah.
two copies of the same thing.
Yeah.
But if you take any Y that's not equal to that and you add Z to it, it's not gonna be the language.
Yeah.
That's guaranteed, right?
So you just take, at least what I did.
Yeah.
Is I took you take any two X and
Yeah,
Y.
but what about this?
Yeah.
And
What
then,
about 10? The resulting string is its own reverse.
oh shit.
Yeah.
But that could be your X, and then you can take a Y, which anything that's not equal to that, and then add the reverse of this, and it's guaranteed not to be equal to it. So it's gonna work. Like if you take the reverse of this to be Z, and then whatever.
Let's
Y
carefully read the My Hill Nero definition, because I think I'm pretty sure I know what in the definition will save us. Okay, so I want, where is it? Okay. Where is, oh, right invariance, blah, 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 and for all you equals Z. It's because you need to consider multiple different Z. Right?
Oh, because it's for all Z.
It's for all Z.
Got it.
Gotta think carefully about quantifiers on these sort of
Yeah.
questions.
Okay.
So notice that you can't really pick a fixed Z and be home free,
Mm-hmm.
right? Because if you pick the string itself, then there might be something like this, right? Because if this is X
Mm-hmm.
and this is Y, then either of these put in front of this Z will give you something that is the reverse of itself, right? Because,
Yeah.
oops, 10101 is in the language, but 10101 is also in the language,
Yeah.
right? This one is XZ, and this one is YZ. So this Z did not work for, this Z didn't do what you wanted it to do, right?
You do YZZ.
Yes.
But then, how do you show? And sorry, I don't want to keep you because it's stuff.
No, that's fine. I can take just a couple more minutes. Let's see. So the let me think.
Since if you're trying to show it for any X and Y, that for all Z it doesn't hold.
I think the thing that I like the most is actually, is there a fixed Z that works? I think there is actually. Oh, I mean, I see a simple-ish way to do it. There might be a simpler way, but
Each word is in its own equivalence.
okay. So no matter what Z I pick, where it's just copies of X, will it always be a reflection of itself? So if I pick Z to some I, like this Z to some I, for example,
Yeah.
or the K. I don't want to write it as a specific Z. Any Z of this form, though.
Yeah.
And let me stop writing sideways.
Mhm.
Any Z of this form this will still be in the language
Yeah.
when you put it in front, right?
Mhm.
That's a good start.
Yeah.
Why are you done now?
This makes no sense.
Well, my first thought is something to do with the length, but I don't think that.
The length would be good. Because you can force the reverse to be in a particular location, essentially. Let's see. Yeah. Let me make sure I'm not being you down too complicated the road, but I think this is fine. Yeah, he's gonna have to do something similar, I believe. Ooh, it looks deceptively simple. The first, when I looked at it at first, I was like,
Yeah.
yeah, your answer's right. No, it's a little more complicated than that because of this problem.
Because you're forcing it to be in the first, like, Y. There's two sets of. This is frustrating.
Let me read his and see if I can give you any other. Now suppose
Why can't you use the like K? Why can't you have K be like based on the length somehow of X? Cause
Oh, you definitely can.
then you have X reverse at the end. Or-
X reverse at the end. X reverse S is going to equal itself always. So there's no point in ever reversing X because it equals itself by definition of it being in the language, right? Though every string is its own equivalence. Yeah.
I mean, yeah, but then okay. Sorry, I'm like.
No, it's fine.
Not well formed.
It doesn't need to be. It's office hours, not the homework. Oh yeah, I guess X doesn't necessarily need to be its own reverse. Sorry, so the idea of putting X reverse at the end is a very good idea. Yeah. Because think about this. Like, this still has its own equivalence class, right? Like, this Z still works for it, right? And this Z will still, like when you upend it,
Yeah.
it will still be its own reverse. So yeah, you may using the reverse of X makes a lot of sense, maybe. And then dealing with the using the length of X and Y to somehow define Z's could be very helpful. Is very helpful. I'll just give you that much. Does that make some sense?
Yeah.
Okay,
Yeah,
so I think that's where I'm going to end for today. Hopefully that,
Thank you.
I think that
Sorry.
at least saved you guys from this answer.
Yeah, thanks so much.
But I don't really have time to dig too deeply into the meat of it. Yeah.
Thank you.
No problem.
I feel like this piece that's harder than the last one.
Yeah, I know. I wish I'd
Just
actually.
after the midterm.
Yeah, I'm sorry my explanations were a bit meandering because I had
No,
not
you
looked
did
at this
great,
carefully.
thank you.
But
Oh, that's
hopefully it
probably
was still.
why it's harder, because we didn't have a piece at last one.
Didn't have pizza. I've just been looking at the midterm, so I didn't really look ahead. And I probably should have at the set. But I think 3 is still going to be hard. I think, but at least I think it might be doable now for you guys because we've talked a lot about it. 1, at least you guys know the obvious misstep to take and all the
Yeah.
pitfalls, and from there should make it at least easier to not make a misstep.
I'm not convinced about the 0 to n minus 1. That's where
0 to n.
figure out.
Yeah, that will. Yeah, that's a good thing to think about.
Are you gonna upload this today?
Hmm?
Are you gonna upload
Yeah, I can upload it today. If I don't upload it today, bother me via email. But I should upload it. You know, so I had problems with YouTube's uploading process a couple times, but don't feel bad about like bothering me in the evening if I haven't, because then I'll either upload it that evening or the next day when I see the email and I'm like, oops.
Thank you so much.
No problem. Have a good one.